7 days ago, an Electron rocket lifted off from Pad B at Rocket Lab Launch Complex 1. Now we're back again, this time from Pad A, preparing to launch a dedicated mission for the European Space Agency for the very first time. We're counting down the minutes to lift off for this Daughter of the Stars mission at 22:14 New Zealand Daylight Time, or 10:14 AM European time for today's satellite operator in Europe for the Celeste LEO-PNT demonstration mission. My name's James Rattray, and alongside Kim Thompson here, we're joining you from Rocket Lab's Mission Control Centre to take you through this evening's launch.
Thanks, James. Well, it is a cool and calm evening over New Zealand's eastern coastline, and all systems across the rocket, payload and range are looking clear for an on-time launch. Tonight we are launching 2 demonstrator satellites called IOD-1 and IOD-2 to a 510-kilometre low Earth orbit for the European Space Agency. These are to test new location, direction and timing services from LEO. ESA's name for the mission is Celeste because this new system in low Earth orbit is being tested to ultimately support Europe's current navigation system in medium Earth orbit called Galileo, one that's been powering smartphones, mobility and critical infrastructure to over 5 billion users worldwide.
Maria Celeste was Galileo Galilei's daughter, and so with a little symbolic wink to the scientific past, we've called this launch Daughter of the Stars. Let's take a closer look.
The first 2 Celeste demonstrator satellites are ready to launch aboard a Rocket Lab Electron rocket from New Zealand, heading into low Earth orbit at an altitude of around 500 kilometres. This launch will mark Europe's first venture into low Earth orbit for satellite navigation and the first opportunity to demonstrate its benefits for future navigation services. The first satellites are compact CubeSats built across Europe by ESA's industrial partners, GMV and Thales Alenia Space. They've been built, tested and qualified in under 2 years and are now ready for their journey to orbit.
The Celeste mission will be the augmentation of European GNSS, introducing a new layer on low Earth orbit. It will address 3 main pillars. On one end, it will be augmentation of the current Galileo and EGNOS, providing faster and stronger signals. It will also provide resilience and robustness through the introduction of additional frequencies, but also innovative and system as service concepts, like, for instance, supporting indoor navigation.
The objective of the Celeste IOD is to pave the way for a future constellation of navigation satellites in LEO. And to that end, we need satellites that are scalable. They need to be capable to be manufactured at a large scale, at a low cost. And so the size of the satellite needs to be pretty low. And so one of the main challenges that we have is to pack a wide array of technologies within such a small element. We do have to demonstrate a number of technologies that includes an autonomous orbit determination and there's a capability to transmit in different frequency bands. And the objective ultimately is to demonstrate the service with a wide range of users on the ground.
Celeste is the first initiative of Europe for LEO-PNT, positioning, navigation and timing for low Earth orbit, supporting previous initiatives from European Union, Galileo and EGNOS. This is bringing the demonstration of new resilient capabilities for navigation in the future. And this satellite is the first step in a long journey that will bring navigation in Europe stronger and more resilient.
These first 2 Celeste demonstrator satellites will broadcast navigation signals in L-band and S-band and operate in orbit for at least 6 months. More advanced satellites will follow, testing additional signals and services until all demonstrator satellites are in orbit. By flying closer to Earth, low Earth orbit satellites can deliver stronger signals and greater diversity of applications. Celeste will test navigation where it is needed most, in cities, challenging environments and regions where today's systems struggle. It will also explore how navigation can work with future communication technologies, including 5G and 6G. Celeste will help elevate the future of Europe's satellite navigation capabilities. Celeste, enhancing resilience to tomorrow's navigation.
A European mission that is integral to the future of Europe's satellite navigation capabilities, riding to space on Electron. It's an exciting moment for the team, and we can't wait to help secure the future of LEO-PNT for Europe with our launch of the mission's first 2 satellites.
All right, with 14 minutes and 44 seconds in the countdown to liftoff, we're now just moments away from our launch team beginning the go, no-go poll for this mission. Our launch director today is Julia Wembacher, who'll check in with each station lead on whether their systems are operational and ready for flight.
Starting with RCC at our launch site, we have LC1M at the top of your screen there, who oversee the entire launch site. Down from them is IT support, and across the row we have our support roles for our launch director and avionics operator. In front of them is mission management, who are the glue between customer and rocket. And in the very front, we have our GC operator, and they're responsible for all of the mechanical ground control systems at the launch site.
Pivoting over to mission control now from front to back, we have ICE, our instrumentation and control engineer, Met, our weather officer, providing us with the latest data from weather balloons and forecasting models, and then flight analysis. Further down the line, next to them, we've got avionics, VCON, and T1, or telemetry 1. In the next row back, we have our hardware in the loop operator, and they're running simulations using that latest meteorological data almost all the way up to launch. Next to them is the GNC team, responsible for the guidance, navigation, and control systems of Electron, and they're also the folks that design the missions and trajectories that help our customers get exactly where they need to be. Down the line, we have our stage operators, and they're monitoring Electron's propellant tanks and feed systems, and then PLS, or propellant loading specialist, whose primary responsibility is loading the propellants to Electron's 2 stages. Finally, in the back row, we have our New Zealand Space Agency representative, Launch Safety Officer, or LSO, our launch director, Julia, ComOps, who's our information and communication specialist, and then finally, our executive team representative for this launch.
Now, each station is about to report either go to proceed onward with launch preparations or no go if a delay is needed. With a clean run through the poll, that will mean that we're ready to move ahead with the count and into the final 10 minutes or so before liftoff. The go, no go poll should begin right at T-minus 12 minutes, so let's listen in to mission control now.
To all operators, LD and mission code, we are proceeding now with the go-no-go sequence, starting with stage.
Stages go.
Avionics.
Avionics is go.
GNC.
GNC is go.
VCON.
VCON is go.
T1.
T1 is go.
GC.
GC is go.
PLS.
PLS is go.
RSO.
RSO is go.
MET.
MET is go.
MM. MM is go. LSO.
LSO is go.
LD sub. LD sub is go. The go-no-go sequence is complete. We are currently T-minus 11 minutes and 3 seconds and counting. We are go for terminal auto sequence at T-minus 10 minutes. From this time, the 3-way procedure is in effect.
Fantastic news out of Mission Control for the Daughter of the Stars. The launch team is cleared to proceed in the final few minutes of the countdown before Electron's flight computer begins the auto sequence for liftoff. Now, a reminder, our launch time today remains 22:14 local New Zealand time or 09:14 UTC. For our European viewers, that's 10:14 AM CET, and then across the United States, we'll be lifting off at 5:14 AM Eastern or 2:14 AM Pacific.
Now we have a 1-hour launch window today for this mission. Electron's launch is scheduled for right at the top of that window, with backup opportunities through to 19 minutes past the following hour, in case we do need to try again for any reason.
As the countdown continues, here's more about the Electron rocket launching today's Celeste mission. Electron is the world's most frequently launched small lift rocket, flying from its dedicated launch pads both here in New Zealand and on the United States' eastern shore. Now, across its 2 stages, kick stage and payload fairing, Electron stands about 18 metres tall, and when it's fully loaded with its liquid oxygen and kerosene propellants, the vehicle weighs 13,000 kilograms. Both stages burn through the entirety of its propellant in less than 10 minutes of flight before the kick stage that's connected to ESA's satellites is released to complete payload deployment for the mission.
The majority of the vehicle is made from carbon composite material, which is why Electron has that sleek black look. The strength-to-mass ratio of carbon composite is particularly beneficial for small rockets like Electron, which was the world's first carbon composite rocket to reach space when it made its debut almost 9 years ago. Another world-first technology on Electron is its Rutherford engines, each one of them made with 3D printing and powered by batteries. There are 9 of these engines at the bottom of the first stage and a 10th engine on the second stage, with some slight modifications for the vacuum conditions of space. Within its kick stage platform on top of the second stage is another one of our 3D printed engines. This one is called Curie. It powers the kick stage and attached payload to achieve the target orbit with an accuracy of within mere meters.
And this mission will be our 85th launch overall and 6th for this year off the back of Electron's busiest year yet in 2025, deploying missions that built constellations monitoring disasters, connected devices around the world, supported national security and defence with hypersonic flight tests, and delivered satellites to space for international space agencies like today's mission. Here's a little bit more about ways that our Electron rocket delivers access to space for everyone.
One of the advantages to having a dedicated mission with Rocket Lab is everything is tailored to your needs as a customer. Instead of going on a rideshare mission where your priorities might take a back seat to other customers, you are in the driver's seat of your mission. The difference between booking a dedicated launch with Rocket Lab and booking a rideshare service on a larger rocket is basically like the difference between taking the bus and taking a black car service. We can put you exactly where you want to be in orbit so that you can start operations on day 1. So you might not need to include a large propulsion system on your satellite in order to orbit raise or phase change. We use the kick stage for precise orbital insertion, so we can put you exactly where you want to go. If you need to show results from your satellite, whether that's proving technology or showing value to investors, you really need to be able to turn that around very quickly. And if you're going with a dedicated option, we can guarantee that for you. With Rocket Lab having 2 launch pads and 132 launch opportunities approved per year, it really changes the game for the amount of flexibility that we're able to offer for customers. You're never going to be forced in a position that puts your satellite at risk. We've had so many instances of a customer processing at the launch site and encountering an issue that they need to look into further, and we say, no problem, we will pivot to the next customer, we'll get them going, you guys stay here, keep working, and then once you're ready, we'll put you on the pad as soon as you're good to go. That's the kind of flexibility that basically no other launch provider in this industry can offer. It's amazing to see that in less than 10 years, we're knocking on the door of 100 launches. And it's great to be able to help guide our customers through a process that has been proven over that amount of time and with that amount of heritage. You just don't see that in this industry that often, where you've got a provider that's able to execute so quickly and reliably. The best feeling in the world as a mission manager is when you get to tell your customer, here we've successfully deployed you in orbit.
Payload deployed.
It's been almost 9 years since Electron's first launch back in 2017, and it's been incredible to be part of some of those important missions that make up our history. Now with this 85th rocket on the pad, ready for launch, we're only a few minutes away from adding another fantastic mission to the list of Electron's achievements.
Now, it's a big deal for us at Rocket Lab to be launching for the European Space Agency, but this mission is also just as big a deal for the agency themselves. Let's hear from the Director General of ESA, Dr. Josef Aschbacher.
Ladies and gentlemen, I'm delighted you can join us today to witness the inaugural launch of the Celeste mission aboard Electron, operated by Rocket Lab. Satellite navigation has become essential to our daily lives. Here in Europe, Galileo and EGNOS are a true success story, powering everything from our smartphones to critical infrastructure. But we can go further. We can make these systems even more robust, more resilient, and capable of so much more. Celeste will demonstrate how a complementary layer in low Earth orbit can enhance Europe's current medium Earth orbit navigation system, delivering stronger signals, new frequency bands, and entirely new services. And this mission doesn't stand alone. Celeste will help shape the future evolution of Europe's satellite navigation capabilities and inform the development of the European Union's own LEO navigation layer. It also contributes to one of the three core pillars of ESA's new European Resilience from Space initiative, endorsed at CM25, which lays the foundations for Europe's future strategic space capabilities. Last year, we celebrated 30 years of satellite navigation at the European Space Agency, a journey that gave rise to Galileo and EGNOS and established Europe as a global leader in this field. Today, with Celeste, we take the next step in shaping its future. Good luck, Celeste, and have a very safe flight.
It's been a pleasure working with the ESA team throughout this campaign, and we wish you all the best in commissioning your spacecraft.
All right, T-minus 2 minutes and 48 seconds. We are just moments away. Standing by now for auto sequence start at T-minus 2 minutes. Here we go. Let's listen into that countdown now.
To all operators, we are go for auto sequence start at T-minus 2 minutes. LDs go for launch.
The vehicle is fully on internal power. AFTS is green and enabled for flight.
Alongside complete, the system is in recirculation. Anti-geyser ring is disabled. Stage 1 and Stage 2 tanks are pressed. High flow engine purge enabled.
T-minus 20 seconds and counting. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1.
Stage 1 propulsion nominal.
A beautiful nighttime launch of Electron from LC-1, and there goes the daughter of the stars on her way to orbit for the LEO-PNT constellation and ESA for the very first time. Now Electron's flight computer will soon command the engines to throttle back in preparation to pass through max Q, or maximum aerodynamic pressure, that moment in flight when the pressures against the rocket are at their peak as it climbs through the atmosphere.
Approaching max Q. Cleared max Q.
And there it is, that's max Q cleared by Electron as it continues to orbit. The 9 Rutherford engines at the bottom of Electron's first stage are keeping that mission on track, now at more than 2,500 kilometres an hour, well above 20 kilometres in altitude.
In about a minute's time, we're expecting to see those engines power down completely to allow for a quick series of events across the vehicle's first and second stages. Engine shutdown is called MECO, or main engine cutoff, and it happens just a couple of seconds before the second stage is released along its flight path to allow for a clean separation of the stages.
Then the single Rutherford engine on the second stage ignites to continue along that trajectory and build up enough velocity to achieve orbit. 3 events coming up in quick succession, so let's check back in with the operators for confirmation.
"15 seconds to staging. Entered burnout detect mode.
MECO confirmed.
Stage separation confirmed.
Stage 2 ignition confirmed.
Nicely done by Electron. As you've just heard, that was MECO, stage separation, and second stage ignition for Daughter of the Stars. Electron's speed and altitude are looking nominal as we approach fairing separation, when the nose cone covering the IOD 1 and 2 spacecraft will split in half and leave the vehicle.
Fairing jettison confirmed.
A nominal separation of the fairing for Electron, and for the first time, ESA's 2 satellites for its Celeste mission are exposed to space. All up, the flight time for the second stage is about 6.5 minutes to achieve orbital insertion. Now, we've got a couple of minutes between now and our next milestone event for the second stage, called the battery hot swap, scheduled to take place at around T plus 6 minutes and 32 seconds. Otherwise, everything is looking nominal across Electron's performance, which you can track by our speed and altitude dials in the top right-hand side of your screen.
Stage 2 propulsion holding nominal.
All right, a minute to go before our next milestone event for the second stage, the battery hot swap. Now, our propulsion system uses batteries to feed propellant into the Rutherford engines. And since the second stage engine burn lasts longer than the first, it starts with several battery packs to power its electric pumps. But as that engine burn continues after the first packs are drained, carrying dead batteries is inefficient.
Yeah, so Stage 2 propulsion system instead switches to the newer battery packs for its power source and gets rid of the old ones without interrupting the engine. That is why we call it the battery hot swap, and you can sometimes see the old battery packs on your screen as they're dropped from the vehicle. So keep an eye out for that moment around T plus 6 minutes and 32 seconds while we listen in to mission control at the same time.
Guidance is nominal, 200 seconds remaining.
HVP discharge holding nominal, approaching hot swap in roughly 30 seconds.
Throttling down. Battery jettison confirmed.
Beautifully done there with both the visual and comms confirmation that battery hot swap was successful for Electron's second stage engine. This fresh pack will power the vehicle for another 2.5 minutes while we continue to increase our velocity. Then the second stage will separate from the kick stage that's carrying the ESA satellites, sending it on its way to reach orbit and completing the first phase of the mission for Daughter of the Stars.
HVP discharge holding nominal.
The second stage operations are complete. Electron's kick stage is released into a nominal transfer orbit, which is exactly where we expect to be. Now, this transfer orbit is typically elliptical, which means that our lowest point and highest point are actually different. So, to reach the mission's desired final circular orbit, the kick stage actually needs to maneuver ESA's satellites into position. But first, we need to reach that nominal transfer orbit following separation from the second stage, which is coming up in about a minute.
Yes, what we'll see there is Electron complete the same actions for the second stage as it did with the first. Instead of MECO, though, we'll have SECO on the second stage. The Rutherford engine will shut down before separation of the kick stage from the second stage puts it into that nominal transfer orbit we just talked about. It's another quick sequence of events, just 4 seconds or so in total, and it's scheduled to take place at T plus 9 minutes, so let's listen in.
Entered burnout detect mode. Guidance is in terminal, 20 seconds remaining.
SECO confirmed.
Stage separation confirmed. Nominal transfer orbit achieved.
Excellent work there by Electron. That's SECO and kick stage separation confirmed, with ESA's satellites off and on their way soon to begin their mission. Just under 10 minutes work on your screens there, but months of work by the ESA and Rocket Lab teams coming together for this monumental launch.
Now, before we reach payload deployment on this mission, the kick stage's journey around Earth takes about 40 minutes or so before it's in the right place to deploy ESA's satellites. During this time, we're out of ground station coverage for the most part, so we're going to take a break in the broadcast for now, but we'll be back to see out the final moments of the launch before the Celeste mission begins for ESA with payload deployment. Join us again soon.
Hello and welcome back to the broadcast for Daughter of the Stars, our Electron launch for the Celeste mission by the European Space Agency to test navigation technologies in LEO for a future European constellation. We had a successful liftoff today at 22:14 local time from LC1 in New Zealand, completing all the usual launch milestones by Electron to reach the last phase of the mission, deploying the satellites to their final orbit.
Well, while we were off air, Electron's kick stage, with ESA's satellites on board, completed its nominal transfer orbit, travelling around Earth before lighting its engine to reposition into a circular orbit at 510 kilometres in altitude. We are listening out now for the end of that Curie engine burn from our operators in mission control, which will then mean we're only a matter of seconds away from the first of 2 payload deployments for this mission. Let's listen in now for Curie engine shutdown confirmation.
Carry cutoff confirmed.
Nominal final orbit achieved.
There we go. Engine shutdown achieved on the kick stage. Now less than a minute until payload deployment for the first of ESA's satellites, the IOD-1 spacecraft by GMV. Let's follow along.
Payload 1 separation confirmed.
Payload deployment confirmed there for the first of ESA's Celeste satellites, IOD-1. Congratulations to ESA and the industrial team as your mission in low Earth orbit begins.
Next up will be payload deployment for the second and final satellite on board. That deployment is scheduled to take place at around T plus 54 minutes and 6 seconds on the mission clock, so we've got about 3 minutes to go, but a lot can happen in those 3 minutes.
That's right. At the speeds we're going, we'll be travelling approximately 1,500 kilometres over the ground from west of Morocco all the way north off the coast of Ireland. Along the way, our reaction control system will initiate a very specific maneuver to orient us in the required direction for payload deployment. The RCS thrusters on our Curie engine are responsible for our pinpoint accuracy and also allow us to do altitude raising and lowering maneuvers as well as plane changes.
That's right, and we've sent more than 80 Curie engine modules to space, including the Hyper Curie variant used in our Capstone mission to the Moon for NASA. Along with the Rutherford engines on stage 1 and 2, that's over 900 of our 3D printed engines sent to space. And today's 2 spacecraft will take us over 250 satellites deployed to orbit, plus 1 to lunar orbit, all by our workhorse small-sat launcher Electron.
That's right, and Rocket Lab didn't just launch that satellite to the Moon, we built it as well. Our Space Systems team are hard at work on several programs, and late last year, our 2 Mars-orbiting satellites were deployed into space to begin their journey to the Red Planet. They're currently at a parking spot in space at a Lagrange point, awaiting a planetary alignment until they can continue their journey to Mars to measure the planet's magnetosphere. They're currently holding course at L2, which is the same Lagrange point that's home to the James Webb Space Telescope, about 1.5 million kilometres away from Earth. Now, once Earth and Mars align in the fourth quarter of 2026, the twin spacecraft will then use Earth's gravity to slingshot towards Mars.
Okay, let's bring things back down to Earth, or at least a little closer. We're about a minute away from payload deployment for the final ESA satellite from Electron's kick stage. As we mentioned earlier, we'll be firing up the RCS to point us in the desired direction for deployment, and then it won't be long until IOD-2 is released from its deployer. Here's that animation again to see how the second deployment differs from the first while we listen into mission control in real time and getting that confirmation live.
Payload 2 separation confirmed.
Payload deployment confirmed for IOD-2 and confirming full mission success once again by Electron, this time for the European Space Agency. Welcome to space and the beginning of a new chapter in satellite navigation for Europe. The daughter of the stars has joined Galileo in space. Congratulations to the ESA and Rocket Lab teams, our first mission for the European Space Agency and our 85th launch overall for our Electron rocket.
And also a big congratulations to the team at LC1, demonstrating the value, of course, of multiple pads at launch sites around the world. A smooth turn from Pad B back to Pad A, rollout, wet dress, all within a few days. We'll have another mission ready on the launch pad before you know it, so keep an eye on our website and social media channels for updates about our next mission. Thank you so much for joining us. This is Rocket Lab Mission Control, signing off.